if we have to bring our computer with our presentation and nothing else.
No. Of course, you participate in a whole team design, so you are expected to answer questions also on the work of the other teams. So you, for sure, you had interfaces to other teams, you interface to other teams. So at least the teams to which you interface, for sure you will be asked questions, but also to all over for all the satellite. So generic questions, but we will ask you. Okay. Also on other groups, not only your group. That would be too late.
We have only to bring our computer with our presentation at the exam.
With the presentation for the, we will collect all the presentations in one single presentation, and then we will be asked to discuss randomly each point in the presentation. Of course, the general, not with the detail of the people who prepared or who was working in that group. But if you are from structure and I ask something about attitude control or something about thermal, general questions, I'm expected you to answer, not to know only your specific work.
Okay. Thank you.
No problem. Okay. So I see you tomorrow. If there are additional questions, I can answer tomorrow. Okay. Bye. See you.
Good afternoon to everybody. We can start for today. Okay, so we were discussing, and we continue on this line, corrosion phenomena which are based on the electrochemical aspect. That means, for example, atmospheric based corrosion phenomena. And we said that we can have a double approach. The first is defined by a thermodynamic approach, which is able to tell us if any oxyreduction reaction can happen or can't happen. Following this, we have also the kinetics approach, which is used in the case thermodynamics answer is yes, the corrosion phenomena can happen, and which is able to tell us how fast is the corrosion phenomena, that is, how much is the value of the so-called corrosion rates. So if we start from thermodynamics, we can say that corrosion is thermodynamically driven to lower the overall energy of the system. And so thermodynamics gives to us an understanding of what are the energy changes which are involved in the corrosion phenomena under investigation. And if we want to prevent the corrosion reaction, referring to the Gibbs free energy, delta G, we should put our system, or we should verify if our system for that corrosion phenomena, and this, if happens, means that corrosion cannot be established during working condition, if the variation of the Gibbs free energy is positive. So we can say from a thermodynamic approach, remembering which is the formulation of the change in Gibbs free energy, depending on the absolute temperature, depending on the universal gas constant, depending on the reaction quotient. We should say that if the change in Gibbs free energy for that chemical reaction, even though it's an oxyreduction reaction, is positive, corrosion cannot happen. If instead the variation, the change in Gibbs free energy is negative, this means that that reaction is possible, but we cannot predict which is the rate of corrosion for which we need the kinetic approach. That's the basic for the Gibbs free. Together with the concept of the Gibbs free energy, we do have something which has been studied from you some years ago, for example, in the chemistry course, the Nernst equation, which is the second pillar. And the Nernst equation is an equation, obviously, which is able to let us to calculate the potential of an electrochemical cell, being the corrosion phenomena based on two electrochemical cells, one at the anode, one at the cathode. We can calculate the value of the single potential and then understand, and this is obviously linked with the Gibbs free concept, if we do have a driving force in terms of difference of potential, which allow to us to say, yes, that reaction can happen or that reaction cannot happen. The model which has been proposed and which is used because it works from by Nernst with this equation is something which cannot be, let me say, divided by the Gibbs approach, because they are both based on thermodynamic approach. And so we can say that one can be, let me say, derived by the others. And if we have a general reaction in which we have the reactants, two general substances, X and Y, and the products, two general substances, C and D, as it is reported in the fourth part of the slide, that is here, we can write down the expression of the Gibbs free energy variation in the thermodynamic approach, taking into account the gas constant, universal, the temperature, and the activity of the product and reactant with a logarithm before. And this can be also written by having in mind and remembering the Faraday constant, F, the number of electrons which are exchanged during the chemical reaction, and the potential defined by the Nernst equations. So they are linked each to other, and the general expression of the potential of the single corrosion cell defined by the Nernst equation, I remember to you, is E, the potential, equal to the potential which is evaluated in standard condition, which is also tabulated. And then we do have the last terms with, again, universal gas constant, the absolute temperature, the number of charges, that is of electrons, which are involved in the reaction, the Faraday constant, F, which appears also in the formulation of delta G, and then the logarithm of the activities of products and reactant. In our cases, in which we do have not very concentrated solutions, we are talking about electrochemical based corrosion processes. So remember that we said that this kind of phenomena can occur when we do have condensed phases. So when we have not very concentrated solutions, this means that the corrosion can happen, but means also that is not instantaneous, so that the concentration of the products is so high, for example. In our cases, which is also called the case of solutions having a dilution sufficient, the activity can be replaced, and that's another chemistry concept, by the concentrations. And so if you see here, the next equation, for what it concerns, let me say, one reaction like this, general, for example, for an oxidation reaction of a metallic element called N, which give rise to ions in solutions with having N plus as number of oxidation, and thus leaving the same number N of electron. This potential, Nernst equations, remember, very important, he had also the Nobel Prize, is equal to the potential in standard conditions plus the same terms that we have seen before, but just replacing the activity concept with a concentration concept, which can be in some cases, equal to 1 if they are referred, for example, to solid, that is, to solid materials, or to gases, which are in standard conditions. This is the base for the thermodynamic approach. Then we will see in a moment how we can use it practically in order to find our answer. For what it concerns, instead, the kinetic approach, our main parameter is the corrosion rate. And the corrosion rate can be expressed in different ways. Sorry for the Italian, but I will be clear, I hope, just explaining to you. One possibility is to think, for example, to weight variation, this one, of the materials of the component which has been is going under the corrosion phenomena. If we look only to the weight variation, that's not a good approach, because first of all, we need to know we are talking about the necessity to have a corrosion rate for how long time that variation has been manifested. And so first thing that we have to take in mind when we are going to express the corrosion rate, for example, as on the basis of the weight variation of the component that is of the materials, which is going under the corrosion phenomena, is to refer, we need to refer this weight variation to the time. But this is not still enough, because let's say, for example, our system is losing 1 gram in 1 day. Well, the corrosion phenomena, remember, there is a corrosion that happens on the surface of our material. So in terms of severity of the corrosion, which is the aim to define the corrosion rate, the case in which these materials is going to lose 1 gram in 1 day, but with us an exposed surface of 1 square meter, just to give to you an example, is obviously substantially different from the case in which we do have loss of 1 gram on 1 day, but the surface on which this material loss is referred is not 1 square meter, instead, for example, 10 square meter. This means that in this second case, we should say that the severity of the corrosion process, and thus the corrosion rate, is less than the previous case. And so this means that when we need, or when we want to refer as an expression of the corrosion rate starting from weight variation, we need to refer, and this is one example, the weight loss to the surface which is exposed and to the time of exposure. This can be given in terms of international unit measurements or UK unit measurements, in which the length the surfaces are replaced by using the unit of measurement, which is inch. There is also another way, which is quite common, but for which we need to care very much attention to define the corrosion rate, referring to the depth of penetration. What does it mean? If this is our component, that is our surface, and we are thinking that ions are going into solutions, so losing materials on the surface, we can expect that this loss of materials gives a penetration on the exposed surfaces. Thus, for example, means a reduction of thickness. And in this case, when we make this as a basic case, our corrosion rates can be defined as microns per year, for example, in terms of thickness reduction per unit of time, or by using the US or UK measurements in mils per year, MPY, remembering that there is a very simple equivalence to pass from the MPY unit of measurements or micron per year unit of measurements. And remembering that this is also true, that is, that the possibility to put in relationship the weight variation with the resistance to the penetration, that is what we are discussing now as corrosion rate, by these very simple expressions in which take care about the unit of measurements that are used. This formula with this constant is valid if we are going to express the unit of weight lost in milligrams, the density of the materials in gram per cubic centimeter, the surface exposed in square centimeter, and the time in hours. So this means that the unit of measurements linked to the weight variation can be put directly in relationship with a sort of linear expression of the corrosion rate, which is the resistance to the penetration. But which is, that's better, the concept that must be not forget in order to let us use this kind of expression of the corrosion rate. The concept is that this scheme that I have put here on the slide is valid only if we have a uniform corrosion among the 8 possible forms of corrosion we have seen last time. And so you can express and you can use the unit of measurements of corrosion rate, like for example micron per year, only if the hypothesis that the uniform corrosion is existing is valid. Otherwise, we are going to commit a very strong error and a very dangerous error. Think, for example, the case in which we have pitting, so very small hole. So in this case, I mean, we can have some area in which we do not have the pits, so we have no thickness reduction. Some other areas in which we have pits and so thickness reduction. We cannot say that the behavior of the surface is homogeneous. We are not in the case of uniform corrosion, and so in this case, this simple unit of measurements cannot be used. Why, when it can be used, is useful for us? Why, when this can be used, is useful for us, that is the resistance to the penetration? For a very simple consideration, because if you, for example, have in front of you a system which is subjected to a load. Let's make the very simple case. A system which is subjected to a tensile load, so we have a positive stress, we are able to calculate during time how much force this system is able to sustain, which will be a reduced force due to the reduction of thickness which implies a reduction of the area of the resistance area of our component. So this is useful, but it can be used only if the corrosion process is a uniform corrosion process. Then, to add, since we do have also, as we have said, we do have also the explanation of the corrosion electrochemically based phenomena on the presence of ions which are going into solutions and electrons which are left and then consumed by the on the cathode, we cannot be surprised if with the same approach we have a definition or we have the possibility to use as other unit of measurements of the corrosion rate, the current density, which is usually given into this form, microampere per square centimeter, because we do not have very, very high density. Otherwise, this would mean that in 1 second, the materials will disappear. And so in the specialized test, you can find also as unit of measurements of the corrosion phenomena electrochemically, the current density, which can be put also this in relationship with the resistance to the penetration, that is microns per years or mils per years, by a very simple formula, which is reported here, in which again they appears the current intensity, the number of charges of electrons, the mass density of the materials, the atomic weight of the element on which we are going to put our attention, and then a constant which is 0.129 if our conversation, if our aim is to obtain the value in mils per year, or 3.27 if our aim is to obtain the penetration resistance, that is the corrosion rate, with this meaning in microns per years. That's the basic, sorry, of the thermodynamics and of the kinetics. Now, let's understand a little bit better and re-enter in the thermodynamic approach what is going to happen when we do have an oxy-reduction reaction that is in a wet environment, an electrochemical-based corrosion phenomena. And let's have a simple example in which we put in an acid environment, condensed, for example, metallic element like zinc. What is going to happen? What is going to happen is that after a certain time, we see, for example, that the zinc is going to be consumed. We see that at the surface of the zinc, hydrogen is developed. And we see on the bottom of our recipient, in which we have put, for example, this acid-base solution together with zinc, something is formed, and it is formed a salt, which is zinc chloride, if we have got the acidity of our solution by using hydrogen chloride. So we have the reactants that are these, we have the product that are these, and what happened? If we put our attention on the zinc, we start from, at the initial state, before the corrosion is going to happen, with a metal phase. This metal phase, zinc, let's think to pure zinc, has an oxidation number equal to 0. Then, after the corrosion reaction, we have the formation of zinc chloride, in which, being the chloride -1, the oxidation number of the zinc has turned from the 0 value to +2. And this is the first aspect. Have a look instead on the second reactant, that is hydrogen chloride, which is a strong acid. So as you know, it is dissociated into the solutions, giving rise to hydrogen +1 ions and then chloride -1 ions. And have a look to hydrogen. If we start at the beginning, hydrogen ions, they do have +1 as oxidation number. After the reaction of corrosion has happened, we do have the development of hydrogen gas from the surface of our metallic zinc, and this means that the oxidation number of hydrogen has turned from +1 to 0. So we do have a reaction of oxidation, since zinc is going to pass in terms of oxidation number from 0 to +2, and a reduction reaction, since hydrogen is going to pass from +1 as oxidation number to 0. And this is an oxide reduction reaction, which is going to explain to us with an example what is going to happen in the corrosion phenomena. The oxidation reaction is this one, and is called also the anodic reaction, because the anode is the material which is going to be consumed, which is going to be reduced. And the reduction reaction is this one, we have already said, which is the reaction happening at the cathode. Since in this case, at the cathode, generally speaking, we do have electrons left by the formation of zinc ions consumed. Then, to come back to the general equation, these zinc ions, which goes into solution due to the dissolution, that is corrosion of zinc, they can react with chloride -1 ions and then form, you see here, the zinc chloride salt, which is a product of the reaction. Similar mechanisms to this we have described are those, for example, in the same acid-base solution, which can affect the corrosion of iron, or which can affect the corrosion of aluminum. Obviously, the figures, that is the numbers, they will be different. In the case of this reaction of iron, again, we have 0 + 2 and -1, 0 for the reduction. In this case, in the case of aluminum, we have 0 + 3 as oxidation number of the oxidized species, that is aluminum, and +1, 0 for the reduction of hydrogen. So we do need, as we have said also last time, in order to better understand, to well understand, this electrochemical feature of electrochemical-based corrosion phenomena, an anodic reaction, that is the oxidation, because in that reaction, the oxidation number is going to be increased, and a cathodic reaction with reduction, because in this reaction, the oxidation number is going to be decreased. Increase in the oxidation, decrease in the reduction. And we have seen one possible, with this example, reduction reaction, which is called exactly reduction of hydrogen, which is this one. But this is not the only one. They can exist also other cathodic reactions which are able to consume the electron left free from the anode, that is from the anodic reaction. The most important are those here reported. One, in which also oxygen is involved, as well as the second one, also oxygen is involved. And in most cases, unless we put some technological, let me say, aspect of removing oxygen, oxygen is dissolved and is present inside condensate phases, and it can actively participate to the reduction reaction. This fourth case here reported is the case in which we do have oxygen as important element for the consume of electron, in the case in which our solution, our condensate solution, is acid. This one instead is the case in which oxygen is present, but the solution has a neutral feature, that is as a pH value which is around 7. And so you see also here for the fourth and for the second case, as electrons are consumed, and thus this is also a cathodic reaction. In this case here, if we have in mind, for example, iron, and take the case in which iron is going to go into solution in the forms of iron plus, as we have said before, well, iron is going to be oxidized. It leaves 2 electrons, okay? These 2 electrons are consumed with the appropriate stoichiometric balance of the reaction by the oxygen which is present inside the condensate phase, and they are formed as result OH minus 1. So the iron ions which are in solutions can, here we do not have chlorine minus 1, but we have OH minus 1, can react with these oxidryls, that is with OH minus 1, and then they can form, for example, hydroxide, which have the form of iron and then 2OH. And this is iron hydroxide, which when it is hydrated, that is combined, complexed with water, give rise to that to the corrosion product that we know, which is called rust. Apart from this, the most important, that is reduction of hydrogen or reduction of oxygen, there could be also other, let me say, reduction reaction. The concept is that there is something which is able to consume our electrons which are left from the anodic oxidation. If, for example, in our solution they are present other metallic ions, because we have put these metallic ions inside the solution, well, these metallic ions can consume the electron. They can reduce, for example, the oxidation number, but being still ions, or they can reduce, like in this case, M is a general, doesn't mean any specific element, that's a general expression. They can consume the electron and pass to the 0 value of oxidation number. This is the case, for example, in which, when we talk about that, we told that some hard chromium coatings obtained by electrolytic processes by using chromium hexavalent or trivalent, but the standard, the base was the hexavalent in a condensate solution, are able to give the formation of hard chromium coatings, because these chromium hexavalent ions, they can capture 6 electrons, so chromium can reduce to the 0 number of oxidation, to the metallic form, and if this happens on the surface of a general component, we could have coatings based on chromium, metallic chromium, that is the case of hard chromium plating. Well, the equations that we have seen is this one, the Nernst potentials. We are talking about electrodynamics, thermodynamics, specialized by using, let me say, the value, proper value of R, temperature, Z, which is the number of electrons involved, the constant Faraday, and usually with the coefficient which is related to the use of log on a 10 scale, not on an Ampere scale, with the activity, that is concentration, of the oxidized species divided by the activity of the reduced species. This is the standard potential, which is reported in very well-known tables. These equations of Nernst, which, as we have seen, is based on the free energy Gibbs variations, okay, so they are related, allow to us to write down the potential for any chemical anodic and cathodic reaction and say, as an answer, look into the difference of the potential if we do have a driving force to let the corrosion happen. And it's very important because it allows to us to build some diagrams which are very important to have an idea of what is going to happen, which are called poor bed diagrams or voltage, tension, pH diagrams that now we will see. We can write, we said, these Nernst equations for our anodic and for our cathodic reaction. Here you have an example of the Nernst equations written for the cathodic reaction, which is the reduction of oxygen, the reduction of hydrogen, as we have seen before. And in this case, for the reduction of oxygen, in the case we are in a neutral environment, that is this second case here, okay? Neutral or slightly basic environment. Well, if we put the figures inside these general Nernst equations, we can say that for the hydrogen, we have the standard potential, which is assumed to be 0, then 2.3, the universal gas constant. If we are going to put ourselves in standard condition, you see this is 298 K temperature, that corresponds to 25 Celsius. Then we do have, if we look to the expression Z multiplied F, Z is the number of electrons involved, which is 1, because we write this way, but this means that each hydrogen is going to consume 1 electron. F is the Faraday constant, and then we do have the logarithm of the oxidized species, which is H plus, divided the logarithm of the reduced species, which is a gas, hydrogen. In convention, the activity, that is the concentration, is taken equal to 1, as it happens also for solid. And so if we put the proper value of the universal gas constant here, and we remember this basic definition of chemistry, we can write that the Nernst equation to have the value of the potential of the reaction of reduction of hydrogen is equal to minus 0.059, which multiplies pH. With the same approach, we can write the Nernst equation for the reaction of oxygen, and since the A0 value of the reduction of oxygen refer to the standard 0 value for the reduction of hydrogen is plus 0.401. When we put the figures here, we get an equation which is different from the previous one, remembering again the relationship between H plus and OH minus 1 on the pH. The equation gives to us as a result that the potential of the reduction of the of oxygen in terms of reaction is equal to 1.23 volt. Obviously, this is in volt in both cases. Again, minus 0.059 pH. So to calculate the potential of the reduction as well as the potential of the oxidation reaction, we need to know the value of E0. No too much effort, because we know the standard electrode potential. Here it is called V0, but it is E0, it's just the same. You see here, as for the hydrogen, we put as convention 0. You see here, for example, as for the oxygen, we have just the value which has been used for the previous reaction, and we know this E0 value for any reaction that we want to take into care. And what is going to happen? It is going to happen that, and this is the driving force, when the potential of the reduction reaction is higher than the potential of the oxidation reaction, which involves our metallic element, then we have a positive driving force. So this means that the corrosion can happen. And so all what is under here, you see, the 0 value of the potential of the hydrogen reduction can be corroded by the hydrogen reduction. And this means that if we move on this way, we have elements which have an increasingly active behavior. That means an increasingly anodic behavior. They can be, by a thermodynamical approach, most susceptible to corrosion. And if we look here, for example, we find magnesium, a very low potential. We find aluminium, a very low potential. And if you remember when we discussed some time ago about magnesium alloys, which are ultralight alloys due to the very low mass density of magnesium, lower than that of aluminium, we already said that these materials in some formulation is quite interesting for aerospace applications, not hot application, being the melting temperature of materials substantially comparable with those of aluminium, around 660 Celsius. But for cold parts, since from the magnesium alloys, when they are formulated in a way to be useful for precipitation hardening, we can get a very relevant specific resistance or specific modulus due to the lower value of the mass density. But we also said that we do have, for example, in the case of use of this kind of alloys in aerospace, military specification with which tell to us that we need to put some protective coatings on the magnesium alloys, otherwise we will experience corrosion phenomena which cannot be tolerated for the components itself. On the contrary, if we move with the arrow up, this means that elements are going to increase their tendency to be inert, that is to be eventually cathodic, so not consuming themselves, but being area in which, for example, hydrogen reduction can happen if we have some other elements, which is going to be corroded. And also this means that as higher is the value of E0, as higher is the possibility to have inert element, that is, elements for which thermodynamics tell to us that corrosion cannot happen, because we do not have a suitable difference of potential that is positive. We do not have the driving force from a thermodynamic approach from which we can say that the free energy, Gibbs free energy, is going to be reduced. In this case, if the reaction would happen, the Gibbs free energy would increase, and this means that the reaction cannot happen. And at the first line, we found gold, you see here. And so our experience is that gold is not subjected to any atmospheric or electrochemical corrosion because it cannot be corroded by reduction of hydrogen having a lower potential, or by reduction of oxygen having at the same time a lower potential. This discussion that we have now made on figures referring directly to the standard electropotential in standard condition can be done at the same with the same level with the real figures, with the real number of potential, which are calculated by the Nernst equation. That means not only looking to the value of E0, but looking to the value of the potential of the two possible reactions in conditions which are different from the standard conditions, and thus can give to us the indication that we are looking for. Now, how can we use this indication? Let's have first of all a look to this diagram, in which we put on the y axis the potential, and on the x-axis we put the pH value. If we want to report on this diagram the potential of the oxygen reduction as we have brought before, and the potential of the hydrogen reduction as we have brought before, this is the situation. We do have, you see here, we do have two straight lines having the same slope, which is minus 0.59, but starting on the y-axis on two different points. And you see here the oxygen reduction will start from 1.234 volt, the hydrogen reduction will start from 0, and it is exactly what is reported on this diagram. And if we move the pH of the solutions, then we have that the distance between these two straight lines is always the same, since the slope is the same, and it is equal to 1.234 volt, which I remember to you is just the electrolysis potential of water if we want to generate from water oxygen and hydrogen. And these kind of diagrams, which we have now simply designed, simply drawn, simply reported for the two cathodic reaction we are going to investigate, can be completed by putting on the diagram the values of the potential of the anodic reaction, and thus by comparing the potential of the anodic reaction with the potential of the possible existing cathodic reaction, as we have done conceptually here, starting from the E0 value, we can define if from a thermodynamic approach we do have a positive driving force, a difference of potential, to let the corrosion phenomena happen. So we can answer to our question if starting from a thermodynamic approach the corrosion can happen or no. And these are the Pourbet diagrams. Pourbet was a Belgian scientist which has developed this method and has also developed all the for all the elements diagrams, so we do not need to build because they are already, let me say, reported in a specific atlas, is the atlas of the Pourbet diagram, in which for each element, they are referred to element of the periodic table. This is the case of iron, for example, but we will see also other cases. We can give our final conclusion to say which is depending on the potential value, the stable phase of the metal which could behave as an anode. And so the Pourbet diagrams, they divide the space in areas in which we can have stability of ions, for example, from this thermodynamic approach. This means that this area are area in which thermodynamics tell to us that the corrosion can happen. This is one, this is another one, or areas in which, for example, we can have the formation of stable compounds, not ions, like iron oxide in this case, which means that in that cases, since the ion form is not stable, the corrosion, for example, cannot happen. In the case of iron, for example, we can have a passive state. And on the Pourbet diagrams, the two straight line of hydrogen reduction and oxygen reduction are always reported. And so this is an example, some example of Pourbet diagrams that we can have available. And I repeat, they give indication on the behavior of the single elements, not on the alloys. So are for us important because they can give to us an idea of what is going to happen, but they are not referred to the alloys, instead to the elements of the periodic table. Have a look to this, which is the Pourbet diagram for iron. You see the area in which the ion is stable are areas which are some way underlined. And if you see here, if we move on all over the range of the pH value, we do have the possibility to match the stability of the ions. And this means that iron in this condition can corrode. And this match our experience. Then other thing is to understand how fast is the corrosion, that is the value of the corrosion rate. If we move to the aluminum, for example, you see here we have two broad areas in which we have stability of ions, okay? But we do have also an area in which we have stability of a compound not charged. That is an oxide, for example, in this case. And also this match our experience, since we know that aluminium is going to be passivated by affinity with oxygen. Remember the anodic passivation of the aluminium, for example, in condition in which we are around a neutral environment, that is a pH value which are about 7. If we put our aluminium alloy or our aluminum in this case in a 2-acid environment or a 2-basic environment, the aluminum oxide on the surface cannot be formed. They become stable, the ions, and so aluminum can be corroded. And this is also something which fully match our experience. So this is the way in which the thermodynamic gives to us a response, essentially by give us the possibility to use the Purbe diagrams, which are based on the Nernst equations for the cathodic and for the anodic reaction, and for which we must do any work, because the atlas of the Purbe diagrams are all available. But again, I repeat, we do not have now any indication on how fast is the corrosion, for which we need to refer to the corrosion rate, and also in this case, apart from the existence of standardized laboratory testing, which can allow to us experimental activities to evaluate the corrosion rate, but also for the corrosion rates, they do exist specialized handbook which are able to tell us for certain materials, for a certain working environment, according to the experience in the field, how much higher can be the corrosion rate, depending on the corrosion form which can develop. So also in this case, apart from new formulation, we do not have to do too much effort, because the values of the corrosion rate with a specification I told to you before are already known. Obviously, it makes no sense. It makes no sense look for corrosion rates in situations in which the thermodynamics, that is the Purbe diagrams, tell to us that corrosion cannot happen. You will never find any value of corrosion rates if for any corrosion reaction the variation of the free Gibbs energy would be positive. Now, in order to have or to recall, let me say, some familiarity with what we have said up to now, let's make some examples, or simple examples of a calculation, because obviously what we have said can be gives to us mathematical tools which allow to us to make some calculation. I have prepared some examples for you. First example, we need to calculate the it's called half cell potential, that is the cell potential for copper, because it is for just one electron. If we suppose, for example, that 1 gram, like reported in the test, of copper in the form of ions 2+, it is dissolved in 1000 grams of water, which represent the medium in which the electrolyte is dispersed. And the question is, calculate in these conditions which is the potential of this electrolyte. Well, how to solve this? From chemistry, so we need to know some chemistry or recall some chemistry concept. We know that a standard 1 mole solution of copper 2+ is obtained when we add 1 mole of copper 2+, that is an amount equal to the atomic mass of copper, into 1000 grams of water. The atomic mass of copper, as it is reported in the periodic table, is 63.54 gram per mole. And so the concentration of the solution, when only 1 gram of copper is added, must be the concentration, and we use here, you see, concentration, not activity, for what we have said before. 1 divided 1, because it's 1 gram, divided the atomic weight, which is atomic mass 63.54, and so the calculation is that the concentration of the ion copper 2+ in this case is 0.0157 molar. And so if we want to use our Nernst equations, first of all, we can put inside the formula. Here it is already calculated, the coefficient, having made the hypothesis to be a room temperature with a proper value of the Faraday constant, which is a constant, as well as the universal gas constant. And so we have E0, which is on the table we have seen before. Let's find it if it is present. You see here 0.340, and so here we have 0.340 divided per the number of charges, how much, 2 electrons, so 2, and then we have the logarithm on 10 basis of the concentration of the oxidized species, that is the concentration of the copper ions, divided the concentration of the reduced species, which is the reduced species is just copper, just metallic form, and this means that the concentration is assumed to be 1. And then if we put this number here now with the number 2, we can calculate which is the potential of copper. This is one example of using the Nernst equation in condition in which we have not standard condition. Another example. Suppose we want to design a process to deposit, that is to electroplate, to deposit 0.1 centimeter thick layer of copper. Okay, so now we think to have copper in solutions. This copper in solution, for example, consumes electrons and can form a deposit, a coating, onto a surface which is going to act as a cathode. This means this is the surface, the cathode. We have the copper ions which are in the solutions on the cathodes, because we do have a source, okay? On the cathode there are electrons arriving. These electrons are consumed by the copper ions, which can reduce at the 0 form in terms of oxidation number, and then give rise to the deposit. What we can say, how can we solve this simple problem? If we want to produce a 0.1 centimeter thick layer on 1 square centimeter surface area, resulting obviously from this, which must be the weight of copper. The weight of copper is quite easily calculated if we remember which is the mass density. So we have 1 square centimeter, we do have this mass density, so we can define which is the volume of copper, and so by using the mass density we can define which is the weight of copper. So this is the mass, that is the weight of copper, which is needed in order to have this 1 centimeter thick layer of coating by electroplating. Now we need to remember that there is, for these reactions, of chemical reactions, and that's another chemistry concept, there is an equation which is very important, which is the Faraday equations, which is able to put in relationship the charge quantities, which is the current I multiplied by the time t, with the weight, in this case weight of copper, the number again of electrons which are involved in this case reduction reaction, the Faraday constant F, and the the atomic weight, in this case M, of the elements which are which is under investigation, that is copper. So if we have calculated that we need to deposit a mass of copper which is corresponding to 0.896 grams through this hypothesis made at the beginning, and we put these figures here, pay attention to use always current unit of measurements, just substituting and putting 2 on m, the usual value of the constant Faraday, the value of the atomic mass in gram per mole, we say that we need an electroplate process for which the product of the current with time is 2722 ampere per second. This is not a closed solution, but having these figures, we can say, for example, if we are going to use a 0.1 current, we need, let's convert in hour, for example, but obviously beginning from seconds, around 7.6 hours to get that results. If we use 1 ampere as current, we need more or less 45 minutes. And obviously, higher is the current which is used, that is the quantity of electrons which is available for copper reduction, lower is the time requested. And look at what I have written here, that a current of around 1 ampere with deposition time, that is with processing time, which are around 45 minutes, are not uncommon in electroplating operation in this case. And this is the theoretical results that we get with this very simple approach. Another example regarding the corrosion of iron. And again, by using this Faraday equation, which is very important for corrosion phenomena. The problem is this. Let's have an iron container. Obviously, in this case, we are going to make the hypothesis on our calculation that this should be pure iron container. We know that this is not possible because for our industrial application, at minimum, we use steel, that is iron carbon alloys. But to make a preliminary evaluation, this approach, it works very, very well. So let's have an iron container having a base, a square base with this size, 10 centimeter per 10 centimeter. And let's make the hypothesis that this container is filled to a height of 20 centimeter with a liquid which is corrosive. For example, an acid-based condensate phase. We do have corrosion, so we do have an electrolytic cell. That's general concept. And we see that after 4 weeks in which corrosion is going to be present, the weight variation, the weight decrease of our container is something around 70 grams. We cannot expect, and this is also again the reason because of, apart some special cases, that we have kilograms of iron consumed. Otherwise, we could never use, again, also the approximation of activity with concentration. So they are realistic figures. The question is, calculate a current which was present during this period in order to have these results of a weight loss of 70 grams, and calculate also the current density which is involved in corrosion, in the corrosion of iron. Well, here, we distinguish between the concept of current and the concept of current density. The current density we have defined as one of the possible unit of measurements of a corrosion rate, and the difference is obviously linked just to the surface on which the corrosion is going to happen. And this is one case, for example, for which we can say that uniform corrosion is going to happen. And then when we have calculated, for example, the current density, we can also convert, as we have seen before, the current density in penetration resistance, that is in a corrosion rate with respect expressed, for example, in microns per day, microns per week, microns per year, as it is necessary. So how to solve this problem? First of all, how much is the total exposure time? Well, 4 weeks, it's written, but since we need to take care to our unit of measurements, and the basis is usually to work in seconds. So we need to convert the 4 weeks in seconds. That's very simple, and this is the results. Again, you have seen also before here, okay? If we use as unit of measurements grams for what it concerns the weight, and then gram per mole for what it concerns the atomic mass, the results in terms of intensity of current per time is ampere per second, and so we are just using the same approach. So using the same Faraday equation, now the question is to calculate the current. So in the previous example, we have calculated the product I, the current per time t. Now we just need to calculate the current, and so you see again we are going to use the weight in gram. N is equal to 2. The Faraday constant is a constant. The time is expressed in second. The molecular weight is expressed in gram per mole, and also this is reported in the periodic table. Just making this simple calculation, the answer to the first question is very easy, is 0.1 ampere, and so this is the current. Now, if we want to convert, and this is the real reason to have the value in terms of current density, because current density is the unit of measurements of our corrosion rate, again, because we can have 0.1 ampere as intensity of 1 meter, 1 square meter of surface, or 10 square meter of surface, or 100 square meter of surface, and obviously the reduction in thickness being in this case a uniform corrosion process, that is the severity of the corrosion phenomena is different, decreasing as much as the surface is going to be increased, and as we need to take care of the surface and the measurements in terms of current density. But well, also this is very simple, because just make a calculation of the total surface of iron which is in contact with this corrosive liquid, and according to the dimensions that we have said before, because we do have a square based container filled up to 20 centimeters, and so we need to take care of this surface, of this surface, of this surface, of this surface. Then we can say that the total exposed area is 900 centimeters, and you see here we found the answer to the second questions, in which we have, according to the unit of measurements that we have used up to now, 1.1 essentially multiplied by 10 to minus 4 ampere per square centimeter. So from this you also can see how it's reasonable to have as unit of measurements, as I said to you before, micron per square centimeter, because otherwise we have too many zero in this case, and so it would be something with around 111 micron per square centimeter. I prepare for you also other examples, but since this example is going to introduce to us a very important corrosion form that we have mentioned and which cannot be neglected by an expert engineer, that is the galvanic corrosion, I think it's better that we make this example and then we start the galvanic corrosion in the next lessons. They are 3:30, so I think we have finished for today. Let me just remember to you, as I said to you last time that next Friday there will be no lecture since I must go back for the second vaccine dose, and so we will meet again on Monday of next week. So I'm going to interrupt the sharing. If there are questions, I'm here to answer to you.
Prof, io vorrei fare una domanda.
Pronti?
No, non mi è molto chiaro quando abbiamo visto dalla tabella che ha presentato lei, per esempio prima sulle reazioni, quando ha spiegato il motivo per il quale per alcuni elementi abbiamo sfruttando la tensione,
Sì.
cioè nel caso in cui ci sono casi in cui può avvenire oppure no, sulla base del valore che ci esce fuori.
Allora, se io ragiono solamente, e questo ragionamento poi lo posso fare sui potenziali veri, cioè con l'equazione di Nernst completa, d'accordo?
Ok, sì.
Che però non sappiamo quant'è perché dipende dalle condizioni, quindi la tabella dei potenziali standard, quella è fissa perché sono misurati con riferimento all'idrogeno, per il quale per convenzione è assunta uguale a 0 il valore del potenziale. Il punto è abbastanza semplice: quando il potenziale della reazione catodica, e quindi per esempio quella dell'idrogeno o per esempio quella dell'ossigeno che stava citato nella lista, è maggiore del potenziale della reazione anodica, siccome tu devi ragionare in termini di differenza di potenziale e devi fare potenziale della reazione catodica meno potenziale della reazione anodica, se fai 0 meno qualche cosa diviene positivo, quindi c'hai una differenza di potenziale positivo, la reazione può avvenire. Al contrario, se prendi un elemento che invece sta sopra in termini di E all'idrogeno, quando fai il potenziale della reazione catodica meno il potenziale della reazione anodica, ti viene una differenza di potenziale negativa, il che vuol dire che la reazione non può avvenire, e che significa sostanzialmente: in questo secondo caso avrei un aumento di energia libera di Gibbs, mentre nel primo avrei una diminuzione di energia libera di Gibbs, per come è definito Nernst in relazione con Gibbs. Quindi la parte sopra è quella in cui si dice che io ho un incremento della tendenza alla reazione al comportamento catodico, cioè a non corrodersi, perché il catodo non si corrode, al catodo si consumano elettroni, mentre la parte sotto è quella che fa riferimento invece a elementi che hanno una tendenza maggiormente crescente a diventare anodi, cioè a corrodersi. Questo se tu lo prendi in riferimento all'idrogeno, ma questo discorso lo si può fare anche con riferimento, che è proprio il concetto della corrosione per contatto galvanico, a due elementi metallici